In this section, we'll talk about an important theorem concerning the polynomial equations in the finite field. As before, K is a finite field with Q elements, where Q is a power of P. So the characteristic of K is P. Now we state and prove an important theorem due to Chevalley-Warning on the cardinality of the common zeros of polynomial equations over the finite field K. Let f sub alphas be polynomials in n variables over K. Such that the sum of their degrees is less than n. And we let V be the set of their common zeros in K to the n. Because f alpha is a polynomial in n variables, so its root can be considered as a n vector in Kn. The Chevalley-Warning theorem states that the cardinality of V is congruent to 0 mod P. Now let's prove this. We put the polynomial P as a product of 1 minus those s of alphas to the power q minus 1. For x in Kn, if x is in V, which is a common zero of all such polynomials, then each f alpha is equal to 0 at x. So this product is just a product of ones, which means P is equal to 1. Now if x is not in V, then one of them, say of alpha to the q minus 1, is non-zero. And therefore, its q minus 1's power must be equal to 1. Again, we have seen this many times. This is because K star is a cyclic subgroup of order q minus 1. And therefore, that particular factor is equal to 0. So P is equal to 0 at this x. So P is equal to 1 on V and equal to 0 outside of V. What does this mean? This means that P is a characteristic function of V. Or some people may want to call this indicator function. Now I just realized that this little f might cause confusion with this f because this is an integer and this is a polynomial. So to avoid confusion, let me erase this. You only have to know that q is the power of P, and P is a characteristic of the field K. And now let's continue. For every polynomial f in K variables over K, we put S of f as a sum of evaluations of f at points of Kn. K is a finite field, and this sum is a finite sum. We have S of P, where this P is defined like this, which is a characteristic function of V, is the sum of P of x, where x ranges over elements in Kn. And this guy, because P of x is equal to the indicator function of x by our discussion above. So S of P is just the sum of indicator functions for x ranges over Kn. And what does this mean? This means we are counting how many ones are there in this sum. And this guy is equal to 1 if and only if x is in V. So this is really the cardinality of V. But I must emphasize that this equation holds in K, because each element here is an element of K, and K is a finite field. Because K has characteristic P, if you want to write this in a number theoretical way, it should be that S of P is congruent to the cardinality of V modulo P. And you can think of this happening in Z. Therefore, to prove the theorem, remember the theorem states that cardinality of V is congruent to 0 mod P. To prove this, it suffices to establish that S of P is congruent to 0 mod P. Or in other words, S of P is equal to 0 in K. Okay, now let's go back to the statement of the theorem. We realize that we have not used this hypothesis. We have not used the hypothesis the sum of the degrees of f alphas is less than n. And now we will use this hypothesis. The hypothesis implies that the degree of P, which is the degree of this product, and this is equal to the sum of degrees of f alpha to q minus 1s. And this is equal to q minus 1 times the sum of degrees of f alphas. By hypothesis, this sum is less than n. So this guy is less than n times q minus 1. What does this mean? If you recall the definition for P, by definition P is a product of 1 minus f alpha to the q minus 1s. And you can distribute this product and see that P is a linear combination of monomials in the form x to u. Here u will be a vector, because this is a shorthand notation for x1 to u1 dot xn to un, with, because the degree of P is less than n times q minus 1. So the sum of those indices must be strictly less than n times q minus 1 as well. So the sum of u sub i's must be strictly less than n times q minus 1. In order to show that S of P is equal to 0 in K, By linearity of S from its definition, it suffices to show that S of this xu is equal to 0 for any u satisfying the sum of its components is less than n times q minus 1. This is due to the linearity of S. And we claim that this conclusion follows from the lemma on power sums we proved above. Indeed, S of x to u by definition, this is a n-fold sum, and it can also be written as a product for k equal to 1 to n of the sum x sub k to u sub k for u sub k ranges over k. Note that the condition the sum of u sub i's is less than n times q minus 1 implies that at least one summand u sub I is less than q minus 1. For you to see this more clearly, I should write this sum more carefully. This is a sum for I equal to 1 to n. Okay, now what does this mean? If u sub I is less than q minus 1, then we must have q minus 1 does not divide u sub I. So the lemma implies that we are in this otherwise case, which means that sum must be equal to 0. So S of u sub I is equal to 0 for that u sub I less than q minus 1. But if you look at this expression, this S sub x u sub I is just one of those factors. So as long as one factor is equal to 0, this whole product is equal to 0. So this implies, as a consequence, that the S of x to u is equal to 0 in K. Because one factor is precisely this, which is 0. So this product is equal to 0. And we are done. Now let's discuss two corollaries to Chevalley-Warning theorem. If you have a bunch of polynomials over K in n variables with no constant terms, and the sum of their degrees is strictly less than n, then they must have a non-trivial common 0. By non-trivial, we mean because those polynomials have no constant terms. If you just plug in 0, 0, 0, the 0 vector to each polynomial, it will vanish. And that is a trivial common 0 for them. This corollary of Chevalley-Warning theorem says that there exists an additional common 0 for those polynomials. The proof is easy thanks to the Chevalley-Warning theorem. By Chevalley-Warning theorem, we know that because of this assumption, the sum of degrees is less than n. The cardinality of V, well, remember this V denotes the set of common zeros for f sub alphas. The Chevalley-Warning theorem states that this cardinality must be equal to 0 mod p. And in particular, this means the cardinality of V must not be equal to 1. Because 1 is not congruent to 0 mod p. And therefore, V cannot just have a trivial element 0. And whatever additional element in V other than 0 will be that non-trivial common 0. And this proves this corollary. As a special case of this corollary, if you consider homogeneous polynomials, namely each component of that polynomial has the same degree. In particular, if you look at the following case, written as a corollary 2, every quadratic form in at least 3 variables over k has a non-trivial 0. The proof is immediate because a quadratic form is a polynomial with degree equal to 2. And in this case, n is at least 3. So the degree of this just one polynomial is strictly less than n. Here we are just using corollary 1 with one polynomial. And a quadratic form is homogeneous of degree 2. And in particular, it has no constant term. So corollary 1 implies that f has a non-trivial 0. And we can also interpret this corollary 2 using the geometric language. In geometric language, every conic over a finite field has a rational point. And I only need to explain what this exactly means. A projective conic over a finite field FQ is a curve defined by homogeneous quadratic equation in 3 variables. Explicitly, it takes the following form, where these coefficients are from the finite field FQ. And the term rational point simply means a point in the projective FQ3. Or in other words, x, y, z in FQ3 with 0 removed. So this is simply another way of stating corollary number 2. Because this equation has a non-trivial 0, it must have a solution in the projective space. So in geometric language, this says every conic over a finite field has a rational point. And of course, you can write this in more variables, x, y, z, w, etc., etc. but increasing the number of variables doesn't matter. As a corollary 2 states that this is true for quadratic forms with at least 3 variables over a finite field.